Hello everyone, my name is Sergio Quito, and today I will talk to you about the performance-driven dynamical network generation, achieving trade-offs between the minimum number of nodes and the time to control. But let's go one step back. Dynamical networks, they are pervasive in the real world in several settings. For instance, in this case, you can see both a social as well as a brain network. And of course, these networks are not static in nature. There's usually information flowing from, for instance, individuals in the case of the social network, as well as different regions in the brain when the brain is performing a specific task. Now, when we talk about dynamical networks, what exactly do we mean? Well, the idea is to have some sort of dynamics. For instance, in this case, suppose that you are given a network with capital N agents, and each of these agents contains a state that will be encoded as an entry in this vector x, and for instance, agent I will be xi. And the state of that agent at time t plus 1 will be given as a linear combination of the remaining states. In particular, you could assume that this is an opinion being formed, and basically I'm going to incorporate the information from all my neighbors. That said, there's also some additional influence in these dynamics, and that's what we often refer to as external signals or external inputs. And those are here depicted in blue, and basically there are two components to it. There's a B matrix that tells us which states are going to be affected by an input, and the input itself that is described here by U. Now, with this in mind, there are some aspects of these networks that we can account for. For instance, there's this notion of controllability. So what does controllability prescribe? We say that a system or a network is controllable if, given an initial state, we are able to steer the system towards any desirable state through a sequence of inputs over time. And for that, we will basically consider it to have a desirable goal. Now, that said, how can we actually achieve such sequence of inputs? Well, that sequence of inputs can actually be computed from time 0 to time t minus 1, so t instances of time, and they will be given in terms of this so-called controllability matrix, meaning this is a matrix that it composes by the matrix B, AB, etc., up to a capital T minus 1, where capital T describes the window of time we want to do or perform the control. That said, if we look here, basically we can see that, well, there's a kind of condition that jumps to our eyes, which is, well, this matrix here has to be invertible, which means that this will be then achievable if the rank of this matrix, the controllability matrix, is going to be full, meaning that it will be equal to capital N. But notice here that actually there is something different. So here you can see that we have this calligraphic N, whereas this controllability matrix here was just up to capital T. And that is because when we talk about controllability, we often implicitly assume that if it is possible to find such sequence of inputs from point A to point B, that should be achievable in at most capital N steps. Meaning that if I'm going to allow even a further time to control my system, well, it is irrelevant in the sense that if a sequence of inputs exists, it will exist in at most N steps. Therefore, we could actually ask a slightly different question, which is, well, instead of waiting for capital N steps, in particular in networks like these that can actually be huge, well, we may not want to really steer the system from point A to point B in a very large amount of time. We may actually have some constraints in terms of how much time we need to actually perform a specific goal or achieve a specific goal. And that's actually where the notion of controllability index comes into play. Meaning, well, the controllability index is actually the minimum capital T that you need to consider such that the rank of that controllability matrix becomes full. Of course, that, as emphasized here, and we are going to denote this controllability index by tau, will depend on the matrix A and the matrix B. So let's move forward and keep in mind this controllability index that is, simply speaking, the minimum amount of time I need in order to ensure controllability. Now, we are at the point where we can actually formulate the problem statement. And in particular, what we want is to find the minimum number of so-called driving nodes, in other words, the agents, that will work as sort of influencers in a social network, meaning they are the ones driving the network as well as the state of it. And in particular, we denote this by this identity matrix with this calligraphic J, indicating that we only keep the columns of the identity matrix that are labeled or have indices in this calligraphic J set. That said, our problem statement consists in finding exactly the minimum number of driving nodes, such that the controllability index will be at most a calligraphic T that is described a priori. So in other words, we want the minimum number of driving nodes to achieve controllability in T steps. But what about these dynamics? I mean, what exactly is the values for these dynamics? It turns out that this matrix for sure depends on a specific topology of the network, so basically a calligraphic G over here, but then the exact entries that we may consider for the interaction may depend on specific protocols or specific opinions I have from my neighbors and things like that. So it will make a very hard start to decide upon what would be the minimum number of driving nodes upon specific parameters that may not be actually known or may not be accurately known. And that's actually what steers us away from considering the exact parameters and consider something else. In other words, we're going to just assume that either there is no connection, so basically we have a hard zero, or if there is a connection, then it will be an arbitrary scalar. The key constraint here is to assume that all these scalars will be independent from each other. And if that's the case, then what we can do is to consider, okay, let's consider just the topology, the structure of this network, and assume that among all possible matrices that satisfy that structure, meaning that, well, an entry is going to be 0 if the structure of that matrix is going to be 0. And here notice that I indicate structure by this bar A. So basically, this is indicating just values that are either 0 or something different from 0. That said, the objective is still the same. So I want to find the minimum calligraphic J that will maximize over all possible matrices A the controllability index such that it will achieve a desirable target, in this case, a calligraphic T. Good. So as of now, we have a problem statement. The question is, how can we actually solve this problem statement? And that is something that, in order to understand how we solve this problem, we actually need to consider several aspects. And here is the outline for today's presentation. So we will start with some basics in control and structural systems. Then we'll go through some technical results regarding the problem that I just stated. We'll look into some case studies and try to understand what are the implications in the context of both synthetic as well as real networks. And finally, I'm going to discuss how can we actually try to create networks with prescribed trade-offs between the minimum number of driving nodes and the time to control that is captured through this controllability index. And finally, I'll conclude by doing some remarks and point out some interesting questions to explore in the future. So going back to the basics. Suppose that we have this very simple system. Suppose that I give you that xk plus 1 is equal to this dynamics, so this matrix times the previous state, plus the influence of this single input over here. Well, again, I don't really know these parameters, so what I'm going to consider is the structure alone. In other words, I'm going to assume that, well, the parameters that I don't know, they will be just some parameters, some real values. Notice that these real values could actually be 0 as well. Okay, so the difference is between either a 0 here or hard zeros that will be always 0 no matter what. And those indicate, in the context of the network, the fact that two agents, for instance, are not connected. Now, why do we want to do that? Again, sometimes the architecture is the only thing that is available. But there are other reasons why we'd like to do that. So it may seem a limitation to start with, but it turns out that, well, if a system described only by the structure is structurally controllable, and we will make sense of what needs to be in place to guarantee structural controllability, well, it exists a pair AB with the same structure as A bar and B bar that will be controllable in the usual sense, in the sense that we just recapped before. And here is where things kind of become interesting. So this is kind of the definition of what does it entail to actually be structurally controllable, but it turns out that if we are talking about the parameters to take place in reals, well, this statement can actually hold as follows. So if a pair is structurally controllable, then almost all possible pairs that you can form when considering specific values given a specific structure are also going to be controllable in the usual sense. But there's more. So it turns out that there's another reason why we would like to do this sort of assessment using structural controllability. And that is that as these systems grow bigger and bigger, well, we do need to actually consider new strategies to understand these networks. And we are talking about networks, graphs. So the direct way to actually look into this is to actually consider directed graphs that represent these networks. And here you can see that I'm going to represent a directed graph that will depend on the parameters of the A bar and B bar. How exactly? So let's do the following. So for each of the states, and here I have 3 states, I'll create a node with the same label, x1, x2, and x3. And then for all the inputs, I'll create a label and a node as well. Here I have only one input, so I'll just put u1. Now, let's connect the nodes according to information we have available on the matrices. For instance, here you can see that A bar tells you that, well, there's a connection between x1 to x2, so a connection between x1 to x2. Then there's here a connection that will be from x2 to x3, and therefore we have a connection from x2 to x3. And then if I look at the B matrix, it tells me how the input will affect specific states. And you can see here that, well, the U is going to affect the first row, meaning the first entry of the state, which will be x1. And therefore, I'll have one edge from u1 to x1, here represented with this b1, the first entry of the matrix B bar. Okay, so I told you how to connect the structure with these digraphs, but I haven't told you yet how to actually connect structural controllability with some graph properties. And it turns out that there's one major player to actually get to that definition, and that is the notion of input cactus. An input cactus is basically a recursive definition that accounts for as follows. Here you start with a path that contains states, and then at the beginning of that path that contains states, you are going to connect one input. If you have this sort of path, then you say that you have a so-called input stem. And that input stem is the basis of such recursive definition, meaning that, well, an input stem like this is an input cactus. Now, we can then extend this recursive definition by connecting any of the nodes to a cycle that contains state nodes alone. And if I do that, well, for instance, connecting this state here to this cycle over here, that will be also an input cactus. And I can continue to basically augment from any of the nodes now present in this input cactus and connect it to another cycle and so far and so on. And basically that will be also an input cactus. So why is this definition important? Because structural controllability holds if, once I consider the directed graph, you can somehow clip this graph in these input cacti. The terminology we often use is that the graph is spanned by a disjoint union of input cacti. In other words, we clip the graph and all that is left is input cacti that will fulfill this sort of recursive definition that we just introduced. Now, this has been around for a while, but it has kind of hit sort of popularity within network science after this paper came out. So there is this paper, Controllability of Complex Network, that came out and was actually the cover of Nature. And in this paper, there was a profound study in terms of the structural controllability and their usability in the context of different networks. And in this case, they consider the controllability as the original terminology, basically assuming that we have a capital N time steps, where this capital N is the size of the network. Of course, there has been several developments, and there is a really nice survey within the network science community that accounts for several of such developments. But I wanted to pinpoint this study because it's going to be critical later on to actually establish how we are thinking about this problem ourselves. So we are now in the possession of the basics. So now let's see how can we build upon these basics and try to actually understand how to solve the problem that we have at hand. In other words, how to find the trade-offs between the minimum number of driving nodes and the time to control. Well, the first result that we obtain is that if I want to guarantee controllability within capital T time steps, in other words, structural controllability, because I'm just considering the structure of the matrices in a capital T time steps, then I need to guarantee that the digraph will be spanned by the joint union of input cacti, so similarly to what we did with the structural controllability, yet each of these can contain only at most T state nodes. So I'm going now to clip this graph to get these different input cacti, but now I have a constraint. I cannot clip arbitrary input cacti. I need to have input cacti that have at most capital T state nodes. And that's interesting because then we can actually boil down or reduce the problem of the minimum number of driven nodes such that the maximum possible achievable within the matrices within this equivalence class to be such that this goal is achieved, to a much easier to interpret, at least, problem statement that is as follows. So find the minimum number of driving nodes, calligraphic G, such that once I consider the digraph considering those G driving nodes, this new digraph is possible to actually clip in input cacti that contains at most T nodes. So that's exactly what we would like to do. Now, if we do that, there's a question about, well, how easy is it to solve this problem? And if I actually look and try to just take a very specific example, suppose I start with this digraph. Well, I could actually clip it in this way. So I have here these input cacti. So you see a stem and then connected to cycles. Then here again, a stem connected to cycles. In this case, the cycles are just self loops. And in this case, I can see that I have two cacti, but this one on the left has 1, 2, 3, 4, 5, 6, 7, 8, 9 state nodes. The other one on the right has 1, 2, 3, 4, 5, 6 nodes. Actually, yep, 6 nodes. And you can see that the maximum number of time steps I need to control this system is actually going to be the maximum between the two. In other words, it will have to be 9. Yet, this is actually due to the way I selected these input cacti. So I could actually take the same graph and clip it slightly different. So for instance, this node from here would be in these now input cacti, where now the stem is this one, and now we have these two cycles. And in this case, well, before it was 9 and 6, now it will be 8 and 7, which basically means that I can actually control the overall network within 8 time steps. So you can see that there is no uniqueness on the ways to actually cut this, which kind of indicate that there is a highly combinatorial problem underneath. And that's actually a reason why this problem becomes NP-hard. In other words, this is likely a very difficult problem to solve. So what then? It turns out that we looked into this statement and we kind of reverse engineering this statement as follows. So we know that we need to guarantee that we have at most T state nodes. So let's start there. What can we do with that information? Well, what we can do is try to, instead of just try to cut arbitrarily the nodes, maybe let's try to first restrict the number of nodes we can have in such input cacti. In other words, we take a graph. Notice that this graph will not have any input yet, and we do a partition. A graph partition is basically a decomposition of a graph in elements that contain at most a specific number of nodes. And in this case, if I want to divide this graph in 2 partitions, it means that I want to have it with the minimum number of such nodes. And in this case, we get these 2 collection of states. So this one on the left and this one on the right. And if that's the case, then the question is, if I look at each individually, what would be the minimum number of driving nodes I need for each? And as you may imagine, well, first I have to create sort of a cacti where there will be then a sort of state that requires to have an input. So in this case, this will be the 1, because, well, I have here a so-called state stem. And remember, that will be the beginning to then attach an input to create an input stem and then form the whole thing to become an input cactus. And the same over here. So I have here this stem, and then I need to connect an input to become an input stem. So overall, we can get then this configuration. Now, why this is also a nice way to go about this problem? Well, because if I'm thinking about the partitions alone, there has been several studies that show that there are some methods and tools that allow us to actually find such partitions within 3 to 4 numerical suboptimality in terms of the partitions found. Of course, that doesn't tell you directly about the minimum number of nodes that you'll have then to encounter for each of these graphs. There could be a case where actually the split using partitions may actually lead to suboptimality on top of the suboptimality achieved by the partition itself. So keep that in mind, because that's going to be relevant to make a point later on. And how did we proceed next? Well, we have this idea that let's look into these partitions. But we still have to wonder about, okay, so let's see what insights do they provide us in terms of networks. And in particular, let's start with synthetic networks and some of the well-known models for these synthetic networks. So let's start, for instance, with Erdős-Rényi model. And here you have basically different Erdős-Rényi with different parameters. And both graphs here on the left and on the right are the same. But let me start with the one on the left, because it's probably easier to understand. So the idea is the following. On the x-axis, you actually have how much time you have to allow to control. And of course, here I have in log scale. And what you can see here as 1 is basically the size of the network. So basically 10,000 nodes. So in other words, a network has 10,000 nodes, therefore we would need 10,000 time steps if we are able to control it. And then here on the y-axis, what you have is the minimum number of driving nodes. And you can see that if I needed to control my network in one time step, basically there's no other way than basically controlling every single node in the network. In other words, every single agent in the network would have to be a driving node. As I allowed time to increase further and further, you can see that there will be a diminishing in terms of the number of driving nodes required to actually obtain controllability within a desirable amount of time. Now, there are two aspects that are interesting over here. The first is that, well, after capital T equal to 5, these networks actually start decaying slightly slower than before. Actually, there's a sort of exponential decay before, and then there is a slightly different variation. It is also important to notice that actually if I zoom in here, you can see that there are sort of bars here. And in fact, that's because we're actually doing multiple runs of the different methods by reshuffling the labels of the nodes to try to see if we are not getting suboptimality due to the partition method deployed. And you can see that the variation within each of these box plots is pretty much negligible, meaning that there doesn't seem to be much variability between the suboptimality you may get from the partition and then finding the input cacti. So that said, giving one step back, what I see here is that, well, the number of nodes decay pretty fast up to capital T equal to 5. Then around here, actually you are already very well in terms of the total number of inputs you need. So you can see that these will be like when you achieve the 75, 50, 25, and here you're already at the 10% of the total number of nodes of the network that needs to be driving nodes. And of course, if you allow a lot of time, then maybe you can actually achieve your goal by just considering very few driving nodes. Now, what you see here on the right-hand side is actually the same as for all these different 5 curves for the different average degrees, but the difference is that, well, we have a heat map. And this is just to make it more visual in the sense that, well, you need a lot of nodes at the beginning for short periods of time. These will decrease. And then the important thing is to keep in mind these settings where you have like 75 prescribed driving nodes, 50, 25, and 10. And you can see that, well, this is how it evolves. And for different average degrees, you can see that, well, if the average degree is lower, then, well, you achieve a less number of driving nodes by a later stage or in a larger period of time for achieving controllability. So this is kind of what is already expected, although when we looked into this, we kind of only had a snapshot of the very last point. Remember, the controllability that has been explored is the one that we allow for capital N time steps to achieve controllability. Let's look at a different model. Let's now consider the scale-free model. And you can see, again, that in the scale-free model that we have obtained here, we have similar behavior. So basically, it decays really fast at the beginning, but now you see that these networks, they are somewhat more difficult to control in the sense that, well, these curves are decaying much slower. In fact, you can see that even after the whole amount of time, I cannot achieve for this particular network 10% of the nodes as driving nodes to be able to control my network. And again, on the right-hand side, if I look at the heat maps, you can see that, well, the 10% is getting further and further away, whereas previously, they were kind of getting closer to this. In fact, the 75, 50, 25 are pretty close to each other in all the different parameterizations considered, and then the 10% is the thing that kind of starts diverging away. In the scale 3, you can see that the 10% diverges away much faster. In fact, again, for the last bar, doesn't even show up in the figure. So what about other networks? For instance, small world. Well, it turns out that the small world seems to be the one that is the most advantageous to control. In fact, you can see that the decay is still very fast up to capital T equal to 5, but it will decay continuously fast very soon, and in fact, the 10% is achieved at a very early stage. And of course, if the 10% is achieved at an early stage, all the others are also achieved. And you can see that there's not much difference between all these different networks. In other words, different parameterizations within the small world networks. So that seems promising. But when we're looking into these artificial networks, we start then wondering the normal step that follows, which is, what about real networks? How do they look like? How do these trade-offs in terms of the minimum time to control versus the minimum number of driving nodes come together? And here are some of the examples we have explored. We have explored neural networks, both the C. elegans as well as the macaque with 71 regions, transportation networks, and electrical circuit networks. But notice that, well, if I actually compare these real networks and their requirements in terms of the number of nodes that are required to drive and the time to drive and achieve controllability of the network, does not really compare that well with synthetic networks that are of interest or related with such real networks. For instance, you can see here that, well, 10% in this case, it's kind of late, and then here doesn't even show up, and then here also doesn't show up, which kind of looks like a bit what we would expect in the Erdős-Renyi, yet you can see that, well, the variations are different, so the 25% shows up really, really late. Anyway, let's focus on a specific case, and in particular, brain networks. Brain networks have accumulated and converging evidence that structure-wise, they do satisfy and exhibit small world topologies. And this is not news, but then if we actually compare these sort of trade-offs between the driving nodes and the time to control between one particular network, for instance, the macaque neural network, and we compare it again with the small world network, we can see that, well, the percentage of nodes that are required to control do not really match with the small world ones. And in fact, I mean, I can try to zoom in a bit here. You can see that they are different, but now you may wonder, well, it turns out that this network is rather small. I mean, this is 71 nodes, so why would it match with the small world network that is 10,000? Well, we actually explored these networks for actually 100,000, 10,000, and the spectrums are actually very much alike, at least in terms of these key points of the distributions or quantiles. Which then indicated what I have here presented, which is maybe we should try to come up with generative models that are able to capture these specific trade-offs given a real network. So that's actually the topic of the last part of today's talk. So I will try to convey how can we actually use the insights that I just explained you before and try to create a dynamic generation of networks that achieve a specified trade-off between minimum number of driving nodes and time to control. And for that, and that's why I kind of mentioned this paper before, we are going to one of their findings, which is, well, it turns out that structural controllability in n steps is correlated with the degree distribution of a specific graph. And this degree distribution is basically how many nodes are connected to another node. And you can think about the in degree, out degree, but the same correlations exist either way. Now, it is important to emphasize that when these were studied in this paper, mainly they were considering networks that did not have self-loops. That said, the second thing that I need to kind of recap is what exactly do we mean by generating a network? And in connection with this aspect that there is a degree distribution underneath. And in the network science community, there is something called configuration models. For instance, you could start with a network, you can take the degree distribution, and now you could actually consider the degree distribution to create a network. There are different models to do so, Shunglu among other more sophisticated methods. And if I do that, I'll get a new network, which, if I do this simulation several times and take the expected value, I'll get exactly the same degree distribution. And here you get one particular sample or realization of such network. And you can see that this network looks like this, but not quite the same. For instance, you do not have this edge over here. You do not have this edge over here. And of course, that will affect a bit how the degree distribution will look like. Now, it is possible that one run after the other, you get networks that, again, look similar, but they are not quite the same. Yet, if you look at the degree distributions, they are somewhat comparable. And that was something that made us wonder, well, let's combine two things that we have kind of explored. One is these configuration models and the fact that the degree distribution is correlated. The second is actually the fact that, well, I need partitions that have at most these steps. So if for a moment I forget that instead of having a network with capital N nodes, I just replace it by capital T, then there should be a correlation between the degree distribution for a network that has only capital T nodes. So let's try to then build upon this understanding and try to actually build upon another notion from statistics, which is the notion of bootstrapping. So the basic idea of bootstrapping, for those of you who may not have been aware of it, is, well, each time we conduct statistics, we have a population, and then we take a specific sample. Now, it turns out that the sample is always limited, or most of the times it's very limited compared with the population. And it may give you a specific distribution. Now, the question is this distribution fair in the sense that does it really represent the population? Or is it sort of a biased sample that we get for our analysis? One way to actually do this is to consider, for instance, uniform at random, the selection of parts of this original sample, as you have over here, and then basically see how the distributions individually look like. And hopefully, they will all look alike, the exact same. So let's try to then use this sort of bootstrapping idea together with the degree distribution and the fact that this degree distribution is correlated with the controllability of the network in a specific given number of steps. And what we're going to do is, well, what is our population? Well, a specific network. That, of course, if I take this network, I can do analysis on the trade-offs between the minimum number of inputs and the time to control, the same as we have done just before. Now, what we can do is to consider specific samples. And these samples now are actually going to be partitions. So we're going to take partitions of the graph, and for each of these partitions, we're going to look into their degree distribution. And then what we're going to do is, well, now I can just consider the original nodes, but not the original connections, and consider a configuration model to generate a specific network inside those partitions. And hopefully, the degree distribution should be somehow resembling the original one. Because, again, once I consider these partitions, it's just like I consider in any other graph with a specific given number of inputs. States. Great, so that said, this is the building block. So we are going to have partitions. On top of these partitions, we are going to basically sample the edges, and the edges hopefully will achieve the same statistic, in this case, the degree distribution. But that only gives a specific configuration in terms of, okay, this partition is associated with a specific time to control. But I need to try to guarantee that this holds upon all possible times to control. So what we're going to do? Well, we are going to basically start iteratively. So we are going to start in the case where we consider partitions of size 2. Why not size 1? Because then there is no degree distribution. The nodes are not connected to anything. But if we consider partitions of size 2, then we can consider their degree distributions and consider the same nodes and then sample a specific network. And for instance, here we obtain this particular configuration. Now, Once we have this specific realization, we are going to build upon that realization. We are going to discount these edges from another partition that is somewhat more coarse, in the sense that each partition now has more nodes. And these partitions could be, this configuration could be any other, because we are just taking a specific reconfiguration of the partitions. So we are going to discount the edges that we have encountered here from the ones that we have here, such that we are going now to generate remaining edges between the whole nodes in that partition, such that it fulfills a specific degree distribution on the original graph, in the original partition of the graph. So basically we generate it once again. And then we are going to increase the size of the partitions even further. For instance, consider partitions that now contain half of the nodes. And then, again, we are going to discount the connections that you have over here, and then we are going to resample again the edges. And we continue to do that until we consider the whole graph, and we connect the remaining edges in terms of the missing connections that will achieve a specific degree distribution. So this is a very simple procedure. We're just applying the procedure that rely on the bootstrapping notion. And now somehow what I'm saying is, well, if I look at this initial network and I take any partition in this graph, and I take the same partition on the generated network, hopefully the degree distribution will look the same. And that is kind of constrained by this hierarchical method that, well, we start from the bottom and then up. Again, they are not going to be exactly the same. We actually have encountered this network before. So for instance, this edge is not here. So it's not going to be the exact same network. But we can now ask, okay, so did we achieve our goal? So did we actually manage to recreate these trade-offs between time to control and the minimum number of driving nodes? And if we actually look and we plot this graph, you can see that through our generation method and the actuation spectrum that we have encountered for this network, so basically you can see how the number of driven nodes decay with respect to amount of time available, well, they look actually pretty much the same. Again, it's not going to be exactly the same because, well, first of all, these methods are statistic in nature, and this network is pretty small. You may not be convinced about my argument right now, but okay, let's take a bigger network. Suppose that now I consider actually a rat network. So this is a rat network in terms of the brain. It has 503 nodes. And of course, if I look at this one and this one, you cannot see any difference. That would be kind of cheating. But you can see here the adjacency matrix that we obtained for the two networks. And you can see that this is the original one, and it's not exactly the same as this one. For instance, you can see here that there is some sort of a cluster in terms of connections, and that does not exist over here. Okay, so, and there are other points where this does not look the same as well. If you look at this upper block over here, and this one, there seems to be somehow more concentration over here. Great, so how does the trade-offs compare? So you can see that, well, they almost follow exactly each other. I mean, there's a small difference here, but not statistically relevant, and then you can see that the decay follows exactly the same. So it seems that, well, for some networks, we're able to recreate pretty well the trade-offs between number of nodes and the time to control. And the question that follows then is, okay, but why do that? Why not consider other centrality measures that have been used for many years and show that they are intrinsically related and statistically relevant for a set of possible problems, from resilience to dynamics? So we try to look into, if we generate these networks and we got these statistically indistinguishable spectrums in terms of trade-offs, would we get similar statistics, or which statistics would actually be also statistically relevant? And we looked into between the centrality, closeness, PageRank, etc. But the only one that actually satisfied statistically relevant up to an uncertainty level of 5% was actually the degree centrality. Which is not surprising, given that what we were doing is actually try to bootstrap the degree distribution, so the degree centrality will be pretty much the same. But it is, in my opinion, very interesting to see that some of the metrics that may be relevant for other aspects, they were definitely not relevant for the case where we have these trade-offs between the minimum number of driving nodes and the time to control. So that said, conclusion and future research. Hopefully, you'll get the message that it is important to study these trade-offs between the driving nodes and the time to control. It is possible to generate these networks with prescribed trade-offs. And the questions that kind of follow is the usability of such generation models. Why? Because we are talking about dynamic networks, and as such, we need to consider their dynamics, or at least dynamic properties that are of interest, as it is often the case with controllability. So if that's the case, we could actually start wondering about several aspects. For instance, in biology, suppose that you have a C. elegans. We often associate specific regions in the C. elegans responsible for specific tasks. And the neural system doesn't really vary that much, but there are sometimes some variability. So from a biological perspective, we could actually ask if that structure has something to do with specific controllability properties and trade-offs in terms of time to control and the minimum number of driving nodes. We could even try to push it further and think slightly the other way around, which is, let's try to create networks, try to condition the growing of neurons in the C. elegans to create networks that are somehow with equal trade-offs, and then wonder if the C. elegans will be able to perform like any other C. elegans, or will it be defects? Because that would also allow us to kind of split a bit of correlation from causation. We may get a network that is just a bunch of neurons that will be able to have these trade-offs, but it's not a functional C. elegans. That would be interesting to see. There are also other aspects that are important for engineering purpose. For instance, we do have two types of networks. We have the networks that are basically present in nature, and then you have the ones that are man-made. And for the ones that are man-made, are there some lessons to learn in terms of how to recreate these networks? So if we create networks to have implicitly these trade-offs between the number of nodes you need to control the network in a specific amount of time, is there one that is preferable in terms of properties such as security, resilience, privacy, or they are going to be the same? So these questions, I think, are worth it because they will allow us to unveil new insights about how we should then create and possibly maintain these networks. That said, I find it fascinating, this field of structural systems that basically allow you to combine notions from all sorts of fields, from control theory, signal processing, network science, optimization, and so far and so on. And there's a lot that has been written. In particular, I would like to point out that we recently overviewed all the results in the last 20-something years, and there's still a lot of work to be done. And a lot of this work can actually have direct applications in the context of network science, as well as our understanding of these networks. Because ultimately, it's not just about understanding how these networks behave dynamically, but also how can we actually control them and steer them towards a desirable goal. You can also find this presentation at these references over here. And of course, because this is an online presentation, if you have any questions, feel free to reach out to me at this email. Thank you for your attention and looking forward to see you around.